Something that's a bit of a shame in astronomy world building is how incredibly well isolated each individual world is. Each world we've built thus far is its own isolated environment, and there's little interaction between them. Even in the Mantonian system, where worlds are closer, interactions between worlds are mostly limited to resonance and tidal effects, and it's easy to argue that the situation on Idame is entirely inconsequential to the existence of life on Tora, which is in turn of no influence on Sanu. I think it would really augment Project Espa to have some sort of overarching connection between these worlds. So today, let's try to do exactly that. Hello everyone and welcome back to Project Espa. My name is Yiji Online, and in this series I document the progress of my worldbuilding project, Espa. Thus far in the series we have focused on making Espa's star system, a wide separation trinary star system with the sun-like star Ojor at its center, which is being orbited by a pair of red dwarfs at a far distance. Ojor itself has 9 planets, the 4th of which is the gas giant Manta, the system's main Jovian shepherd, which is over twice as massive as Jupiter. Around Manta orbits a sextuple moon system, of which the inner 4 moons are linked in a 1 to 2 to 4 to 8 resonance chain. The irradiated volcanic world of Idame, the dry silicon life-hosting Tora, and the bright cryovolcanic ice world of Sanu. Today we will add the 4th and final world into this resonance chain, the dead world of Hira. Like Idame, Tora and Sanu, the concept of Hira was derived from a procedurally generated space engine moon, and as such, its initial realism wasn't too great. Like the other moons, it was too large and too massive, resulting in an unrealistic density for the world. The idea, early on, was to make Hira a world suitable to colonization by a spacefaring civilization on Espa. For that reason, I littered the world with valuable minerals and gemstones without really researching how these form or how they would actually be valuable to Espan space colonists. Nope, they were just lying around on the surface for grabs. I saw a video on YouTube about a planet made entirely of diamond, so a moon made of emerald would be fine, right? Right? Ugh. Shockingly, emeralds and quartz would not at all be useful to space colonists. This isn't Minecraft after all, and the most valuable resource for space colonists would simply be just water. Not only to drink, but when decomposed it provides breathable oxygen and hydrogen fuel. So yeah, Hira has none of that, but at least there's tons of emeralds. I guess if nothing else, at least the villagers would love it. Like Sanu, Hira needs to be reconceptualized, ground up. First off, Hira is not at all set up to be a suitable world for either mining or colonization. Period. It is bombarded by Manta's radiation, which makes it hard to settle, and rare earth materials are even more rare on Jovian moons like it than they would be on terrestrial planets. So that idea goes cleanly out the window. But what I do want to do is try to make this moon a bit more tied in with the rest of the system. Everything we've built thus far is incredibly well isolated. Perhaps unsurprisingly, but whereas Idame, Tora and Sanu are moons primarily shaped by endemic geologic processes, I want Hira to provide some contrast and also be shaped by exogenic processes. And I think I've thought of a nice way to combine these two into a concept. In the Manta video, we talked about gas giant moon systems and how the mass of the total lunar system should fall approximately between 1 to 2000 and 1 to 5000 of the parental gas giant in most cases. For Manta, the goal was to approximate a mass fraction of 1 to 4000. But now that 3 moons are done, I'm getting a bit worried, as right now we are on track to fall short of even 1 to 7000, which is roughly 7 lunar masses short. Now to be clear, there is no reason why that should be an issue. Maybe 1 or 2 moons got ejected in the past. Maybe the disk got thinned when Manta did its grand tech tour early on. Or maybe the magnetic field cleared out a lot of material. The point is, there are a whole load of possible reasons why the mass fraction of Manta's lunar system could be substantially lower than calculated. The whole mass fraction method itself is less than watertight anyways, but there's more. Additionally, in that video we talked about how the density of moons should decrease for every moon as we go further out from the planet. Density, of course, is mass over volume. So what kinda ended up happening is that the moon's sizes began to follow a curve of smallest moons on either ends and the largest ones in the middle. But that is not at all required. Even in the Jovian system, there is no clear trend of the largest moons in the middle. Heck, Europa is even the smallest one and it's right there. In the Mantonian system, however, this trend is followed to the D, with moons perfectly lined up from smallest to smallest, with the largest ones in the middle. That feels weird, doesn't it? As a matter of fact, if there is to be an absolute pattern of sizes in a perfect lunar system, it would probably look more like this, with smaller moons furthest in and the larger ones furthest out. Remember how I said they essentially resemble miniature planetary systems? Well, you don't really see terrestrial-sized planets in the outer solar system either. For that reason, I feel compelled to tweak the sizes of the 4 outermost moons. Now, again, this is not at all necessary to do, but my pattern recognizing brain is just looking at these moons and immediately seeing a pattern, which breaks the immersion for me. It's a bit too perfect and too artificial to me. To preserve the established densities, I will also increase the mass of the outer moons, which will boost up our mass fraction from about 1 in 7,000 to 1 in 6,000. Still roughly 5 lunar masses short, but at least now my pattern recognizing brain can rest at ease and enjoy the layout of the system as quirky and interesting. So for the new setup, nothing really changes for Idame and Tora, but Sanu, previously the largest moon, is now downgraded to the second smallest moon in the system. The idea behind this is that Tora would have gobbled up more material during formation, leaving less for Sanu to form from. Its concept as a cryovolcanic ice world is safe though. If anything, its features become more pronounced from its reduced size. By keeping the density the same, we can preserve the concept just fine. The next moon, Hira, is now the largest in the system. And you know what? Why not? Let's make it larger than Ganymede so we have the record of largest moon to our name too. And finally, the outer 2 non-resonant moons will also be a lot bigger and more massive than before. But I will talk more about these in future episodes. Okay, with all that established, let's look at Hira's physical properties. It is the new largest moon in the Mantonian system, with a diameter of 5,498 kilometers, which makes it larger than Ganymede, the largest known moon in the real world. And with a mass just short of 3 lunar masses, it musters a surface gravity of 0.19 Gs. Whereas Sanu, at a density of 3 grams per cubic centimeter, still has water constitute a very small fraction of its mass, on Hira, where the density drops to 2.5 grams per cubic centimeter, it is a reasonable assumption that water could make up over 10% of its total mass. This has dramatic consequences for the type of world it's going to be. As for its orbit, Hira is well over 1 million kilometers distant to Manta, being the very last component of the 1 to 2 to 4 to 8 resonance chain linking Manta's inner moons. At this distance, the tidal forces and radiation upon the moon are going to be massively reduced from what we have seen on the moons further in. As a resonant body, however, it still enjoys a very stable, low eccentricity and low inclination orbit around the gas giant. At nearly 3 lunar masses, Hira is the most massive satellite of Manta by some margin. The further out the moons are from the planet, the more of that mass is going to be made up of lighter volatiles, primarily water. Like previously said, a fairly large fraction of Hira's mass will be water, with water ices making up between 10 and 15% of its total mass. In its center would be a small metallic core. Even at its senior age of 5.8 billion years, its large mass and size have allowed Hira to keep its core partially liquid, resulting in a solid inner core which is surrounded by a liquid outer core. Consequently, like Ganymede, it is able to generate its own small magnetic field, upon which we will touch a bit more later. After the core comes its rocky mantle, which extends for the thick of the moon, to then be surrounded by an impure water ocean, which is compressed into solid exotic ices by pressure at the bottom and frozen into solid regular ice at the top by cold, making for a body that is broadly typical of an icy moon. While that may be the case broadly, Hira's ocean is much more extensive, potentially being up to 3 times as deep as Sanu's, reaching hundreds of kilometers below the surface. At such depths, a layer of exotic ices will form under the water pressure at the ocean floor. Whereas on Sanu, this exotic ices layer was small and fractured, limited to only the deepest reaches of its ocean, on Hira it will be dozens of kilometers thick and all-encompassing, forming its own layer in the world's internal composition. Despite Hira still getting a decent amount of tidal forces upon it from Manta, and it having a hot liquid outer core in its center, the thick layer of exotic ices at the ocean floor would prevent heat from escaping into the ocean as effectively as it does in Sanu. This is partially why it has been able to keep its core hot and molten, but this does also mean that the scale of convection currents found in Sanu's ocean are simply not possible in Hira's. Not to say there would be no convection currents at all, it just would not be anything powerful enough to sustain ice tectonics or cryovolcanoes like those seen on Sanu. Nevertheless, the ocean water would be of similar purity and composition to Sanu's, being only about 90% pure, with large amounts of salts and antifreeze components like ammonia and methane dissolved into it, allowing the ocean to remain liquid at sub-zero temperatures. Due to these limited convection currents, tectonic forces at the scale seen on Sanu cannot take hold on Hira. In fact, if we factor in Hira's advanced age, it's questionable any tectonic processes would still function here at all, meaning a much thicker and more stable glacial crust will form here. Cryovolcanism, which on Sanu provided a source of fresh pure ice, would be almost entirely absent here. Without geologic surface renewal, the surface will age and impurities will gradually accumulate over time, which will result in a darker and less reflective surface. Jupiter's moon Ganymede shows clear evidence of past tectonics, with brighter, younger areas and darker, older areas patching across its surface. Today though, Ganymede is no longer experiencing any tectonics, with some of the most optimistic estimates claiming its processes shut down between 400 million and a billion years ago. While Hira has a lot of factors going for its tectonics, its age is thus far advanced that they too would have shut down by now. It's difficult to estimate how long ago Hira's tectonics would have shut down, but it wouldn't have been too far into its past. If we assume it was a bit more recent, say 100 million years ago or so, it would provide for some interesting world-building opportunities. The tectonic faulting and ice plates, though no longer active, would still be visible, resulting in a patched surface like that seen on Ganymede. Additionally, the end of tectonic activity means that the processes which used to erase impact features are no longer functioning, and henceforth, the moon will start accumulating impact features. In reality, this process will begin even well before the tectonics shut down, simply due to how long it takes to erase some craters. And as such, Hira will be the first body we have built to feature craters on its surface thus far. Like the other moons of Manta, Hira is tidally locked, meaning its orbital and rotational periods are the same, having been synchronized over the ages by the tidal forces, so that the same side of the moon always faces Manta. While this is nothing unusual for moons, especially older ones like those in the Mantonian system, in the case of Hira it provides an interesting world-building opportunity when paired with my last moon, Sanu. As documented in the last video, Sanu is a cryovolcanically active world. Its low-gravity environment allowing for its cryovolcanoes to spew cryolava directly into space, and as such, when it orbits the planet it tends to leave behind a trail of impure water ice. In the real world, its analog Enceladus creates a similar belt of material around its orbit, which is responsible for Saturn's beautiful E-ring. Due to Sanu's new lower gravity, this material is able to escape the moon with great velocities. Combined with Hira's powerful gravitational wake, this means this material is mostly dragged outwards from the planet towards Hira. The result of this process is a very faint icy ring between Sanu and Hira, with Sanu ejecting material which is then over time scooped up by Hira. Due to the tidal lock, this irradiated cryolava snows down virtually exclusively on the leading hemisphere of the moon. This is broadly similar to Saturn's moon Iapetus, which has a dirtied, darker leading hemisphere from scooping up space dust, and a brighter, icy trailing hemisphere which has remained cleaner. This is a slow process of course, but could go relatively fast geologically, with the time elapsed between material being ejected and scooped up ranging in millennia instead of millions of years. And as Hira has been tectonically quiescent for a while now, it has since begun accumulating Sanu's volcanic ejecta on its leading hemisphere. While the ejecta is mostly water ice, it is very impure with salts, ammonia and other chemicals. After having traveled through space inside Manta's radiation belts, it's been strongly ionized, creating darker, redder shades. As such, the leading hemisphere, or front of the moon, has become dark red, while the trailing hemisphere, or backside of the moon, has remained relatively bright, creating a strong contrast between the two hemispheres. Thus far in the project, we have been using the following formula to estimate radiation resulting from Manta's powerful magnetic field upon each of its moons. In the last episode, I revised this formula, as radiation drop-off is not linear, but in reality, radiation drop-off is even more complex than modeled by even this revised formula, and the decay factor n will accelerate exponentially as distance to the gas giant increases, starting at a number close to 3.5, then slowly accelerating to a 4, to then rapidly accelerate towards the 12 to 15 range before slowing down again. Since Manta is over 1.2 million kilometers away now, this means the decay factor n is going to increase rapidly for Hira. In the absence of a formula tying n directly to magnetic field strength and distance, it seems reasonable to put n for Hira between a 6 and a 7 maybe, which would yield a radiation of between 0.2 and 0.25 sieverts a day. Or at least that would be the case were it not for Hira's own magnetic field shielding the moon from radiation. Now, as previously discussed, Hira's magnetic field is generated by a small liquid metallic outer core, which is both thinner and closer to the surface, but also more massive than Ganymede's, so it would only be a weak magnetic field. Determining how weak exactly though is a bit of a puzzle. Magnetic field strength degrades with age as the world's core cools, and while Hira is quite senior, it is also massive and has a high density. Combined with the resonance chain it's in, this core has a strong heat retention, allowing the field significant longevity even after 5.8 billion years. This is not a calculated value, but I think a field 2 to 4 times as powerful as that of Ganymede is possible here, let's say on the order of 1 to 3 microteslas. Hira's magnetosphere protects the moon asymmetrically, with far more shielding being achieved near the equator, where magnetic field lines are closed, than at the poles, where magnetic field lines are open. This is known as a dipole, and it is quite normal. Typically, it results in the field being twice as strong near the poles, but more efficient at the equator. This is why Idome and Tora, which have no magnetic fields of their own, exhibit equatorial auroras, while worlds with their own intrinsic magnetic fields trap those particles exclusively at the poles. As such, Hira would have its own faint polar auroras. And of course, the field would also be able to block up to 90% of the incoming radiation, reducing it to only about 20 to 50 millisieverts a day at the equator, while being less efficient near the poles, which would experience a lot more. This is still by no means survivable to humans, but we're getting to the point where robotic probes could in the future explore this world. Hira is the fourth and final moon in the 1 to 2 to 4 to 8 resonance chain linking Manta's inner moons, completing one orbit for every 2 of Sanu, every 4 of Tora, and every 8 of Idome. It orbits Manta over 1.25 million kilometers out with low eccentricity and low inclination, and is tidally locked to the planet. It is almost 5,500 kilometers across, making it not only the largest satellite of Manta, but at nearly 3 lunar masses, also the most massive one by some margin. It's got a surface gravity averaging 0.2 Gs with a low density of 2.5 grams per cubic centimeters, which reveals an icy composition. It is massive and dense enough though to have preserved a partially liquid core, which generates a small magnetic field intrinsic to the moon. Despite being a typical ice world, Hira is neither particularly bright nor white in appearance like Sanu is. This is because, unlike Sanu, Hira no longer has active tectonic processes. While it did have them until as recently as a few 100 million years ago, they have since shut down, and as a result of this, the once bright and icy surface has started to age and become discolored, with the moon having a grey, brown and reddish appearance now. Occasionally, Hira's strong gravitational pull draws in cryovolcanic ejecta from Sano, which due to the tidal lock has resulted in its leading hemisphere being considerably redder than its trailing side, as this irradiated brine snows down there. Hira is also the first moon to have impact features on its surface. With the tectonics that would otherwise erase them now absent, these will only grow more numerous as the moon ages further. At Hira's large distance to Manta, the influence of the Mantonian magnetosphere is considerably weaker here, yielding significantly less radiation than on the moons further in. Combined with Hira having its own magnetosphere, the background radiation on the surface is limited to just a few dozen millisieverts per day. Still quite harmful to humans, but nothing compared to what we've seen on the moons further in. Due to having its own magnetosphere, Hira also has polar aurora, albeit they very faint, while in its sky, Manta appears 14 times the size of Earth's moon. Well then, it's about time we get to the comment of the episode, which is by Tyson Dennis 1016, who asks, could Sano host life? Well, it probably could support subglacial marine life in its oceans, in the same sense that Europa could. Below the ice, it would be shielded from most radiation and could derive metabolic energy from various chemical processes in the ocean. So yeah, it certainly could host life. But that doesn't really mean that it should, and the reason for that is saturation. When I'm building up the universe of Project Espa, it is not just about making cool worlds to me. It is also about creating a cohesive fictional setting, and for that reason I want to apply life extremely sparsely. For example, Sulking could probably also support life, but I purposefully didn't add any life to it. Because in world building life is special, and I don't want to overuse it. There is a scientific angle to this as well, of course. In the Ojoran system we already have two worlds that have native life, namely Espa and Tora. And that's already twice as many worlds than we know host life in the solar system. Personally, I'm a firm believer in the rare Earth hypothesis, which poses that complex life like that seen on Earth is incredibly rare cosmologically. What we do know is that there are a number of worlds in the solar system with the potential for life, like Mars, Europa, and Titan most prominently, but to a lesser extent also worlds like Callisto and Venus. However, as far as we can tell, despite their potential for life, none of these worlds actually have it. And so, when I'm world building, to me it would make sense that the majority of worlds that could have life actually don't. Anyways, I hope that answers your question. And as always, thank you guys so much for watching. Leave a like if you enjoyed it, and if you've made it this far, consider subscribing for more world crafting. Next episode we're gonna tackle the last and first non-resident moon of Manta. So I hope to see you there, stay tuned.